Hi everybody, this is a continuation of the discussion we started on chapter 28, basically the sources of magnetism. And I just want to basically make a clarification on last time when we were in class. Actually, the session was live when we had that discussion. And I just wanted to follow the same argument that was made then, basically that the fact that we assume that somehow a charge when it's moving with a velocity v, and I said that basically it's going to create a magnetic field. What I argued later on is actually based on this picture, we derived basically what looks like it's a formula for the magnetic field created by a bunch of charges moving in a wire. Well, that is actually what the experiment has shown. It has shown actually that current, and if we take an element of a dl, would create a magnetic field. Since we're taking an element dl, so it's not going to create the whole magnetic field, just a part of it. That is, of course, proportional to the current and the properties of the medium, and of course also the dl element itself crossed with the direction, the unit vector pointing from basically the start of where the element is all the way to where we want to find the magnetic field divided by the distance squared. So this law is what is known as a Biot-Savart law. And this is an important law. This is basically based, if you wish, on observation, okay? This is basically the one that we use to argue that a wire that is carrying a current in it and a distance y from it is going to create a magnetic field in there. And we were able to find a magnetic field. I don't want to draw the arrow because actually the magnetic field is coming out of the surface in here, not going in. So it's going to be coming out. On the other side, it's going to go in, provided that the magnetic field is pointing in this direction. So in here, it's going in. From the other side, it's coming out just by basically making the argument based on the right-hand rule with the curling around the current. We found that the strength of the magnetic field there actually is given by, first of all, the properties of the medium times the current divided by 2 pi times the distance y, where this is the distance y, assuming this is an infinite wire. For a finite wire, we found it has to do with the dimensions of the wire, of course. Now, so current basically it creates a magnetic field. The argument that we started with actually was not correct, and I know the book uses it, and some textbooks actually use it to give you an impression that somehow, okay, a charge is in motion is the one, and that's true, charge in motion that creates a magnetic field, but a single charge cannot make current. That's basically what I want to make in here. One charge, no matter how fast it is, you can approximate it to a current, but it is not a current. It cannot be a current. It's like basically me going outside today to Highway 10 and looking at the traffic, and I see a single car moving in the freeway. That is not traffic. That is just a single car in motion. So that's basically what I want you guys to clarify from last lecture. An interesting result. I'm trying to make these videos a little bit shorter so that you can guys take them into a little bit of lump. So I'm gonna make just one point in here, and then we're gonna come back for other points. So basically, one interesting experiment that we can think of is the following. Imagine with me that you have 2 wires hanging from the ceiling, long wires that is, and if you connect the 2 wires in such a way that somehow, let me try to make them, okay, that somehow there is a battery in here, and that battery will force a current through one wire, and then somehow we connect the 2 wires to one another. So the current will flow in one direction and come back from the other direction, and somehow then I have actually have currents flying in opposite directions on the 2 wires that are very long and parallel. Well, experiment has shown that these 2 wires repel one another, okay? And if the currents actually, if I can make an arrangement in such a way that the currents are actually flowing in the same direction, then in this case, it turns out that the basically, I mean, it's not hard to see how that could work. Basically, all you have to do is just have 2 wires still running from and connect them, if you like, to the positive side and then connect the other one somehow to the negative side, and now the current is going to split itself into two wires and then come back again in here when it's going to go back to the negative side. So basically in here, these points in here, the two currents are in the same direction. This is I1, this is I2. Then in this case, when the currents are actually in the did I have it backward? In this case, actually they will attract. Okay, and in this situation they will actually repel. Two currents in the same direction will repel, and two currents in the opposite directions actually two currents in the same direction actually will repel, and two currents in opposite directions will attract. This is kind of a little bit backward than what you normally think in terms of a magnet. Basically, North Pole, South Pole kind of attract to one another, a negative charge and positive attract to one another, and the similar charge or similar poles usually repel one another. In this case, similar currents, basically in the same direction, they will actually repel, and vice versa, two currents that are in opposite direction, actually they will attract. So let's think about how that can, why is that, and let's actually calculate the force between the two wires. So I'm going to take the first case, basically two wires. I'm going to label this one as wire 1, and I'm going to label this one as wire 2, and see from the vantage point of wire 1 that has a current running through it, which I'm calling going in this direction, for example. So it's I1 in this direction, and I2 is actually in the opposite direction. Okay, so let's see here what happens. So I have two wires that are parallel to one another, and one of them has a current running in the opposite direction than the other wire. Well, I1 will create a magnetic field that loops exactly the way that I described it earlier. In other words, it's going to come out from here, and in here it's going to go in. So in this region, the magnetic field created by I1, B1 if you want to call it, is going into the board. So the magnetic field on this point specifically, which is these two wires have a distance d between them, has a magnetic field going into the screen. So that's what we have found. Actually, I can find exactly what B1 in this point due to the wire 1 is equal to mu naught I1 divided by 2 pi times d, the distance between them. So basically, I know exactly its value too. It's not just how strong it is or what the direction it is, but I know exactly how strong it is, that magnetic field created by this charge. Now, the wire I2 now is subject to the force due to this wire. Basically, if I take the length of it in here, I'm going to call L. If I take an L portion of this wire, well, this L portion of this wire will be subject to a force. I know its direction also. Let's see its direction. I have the current going this way. The magnetic field is going into the screen. So the force must be pointing down, pointing away from the two wires. So basically, this is the force on 2 due to the current running in 1. And that force is equal to, well, I2 times L times B1. In other words, this force is equal to the current in the wire, which is I2. I'm trying to find the force on 2. So I have to be concerned with current running into, and then times the length, because remember the formula that we saw in chapter 27 was saying that it has to have with the length of a wire. So I have to take a finite length in here, times the magnetic field in that wire. And the magnetic field in that wire is the same everywhere. So it's a uniform magnetic field. Since the distance is just two wires are parallel, so the distance between them is d everywhere. So basically, this force then, when I sub the value of the magnetic field, then is going to be equal to mu naught times I1 times I2 divided by 2 pi times the distance between the two wires times the length of the wire. I took a finite length, although the formula that I assumed in here for B1, actually I used the one for the infinite wire, meaning that the distance d is much, much smaller than the length of this wire. That's basically what that means. So in this case, I have to we define something called basically the force per unit length, which I'm going to label it F2 on 1, which is just basically the force divided by the length. So the unit for this guy is going to be Newton per meter. How many newtons? What's the strength of this force for every single meter? Basically, that's what that thing is. So it's going to be mu naught, the product of the two currents divided by 2 pi times the distance between them. And it's clear that this force is a repulsive force because of the fact that it's pointing away from the two wires. Now, if I look at it in vantage point of the second wire on the first wire. Okay, for the second wire, it has a current running through this direction. So it's going to be to this direction. So it's going to create a magnetic field curling around in such a way, this pointing here, the magnetic field, B2 is actually into the board and coming out from the other end again because I reverse the direction of the current in this board. So B2 in magnitude is going to be equal to mu naught I2 divided by 2 pi times the distance. But it's going to go into the board. Now the wire 1 has a current running in this direction, and the magnetic field is coming into the surface actually. So this is this situation. Current this way, magnetic field into the screen. So the force F on 1 due to wire 2 is actually pointing upward. So this is F on 1 due to 2. So again, I'm going to take a finite length, which I'm going to call L again, of this wire, because it doesn't make sense to talk about an infinite wire at this point. So the length L. So then again, I'm going to find the force on 1 due to 2 is given by the force on the first wire due to the second one is equal to, again, I1 now. We're talking about wire 1 now. So I1, namely this wire, and it has a current I1 in it, times the length L, times the strength of the magnetic field in that point, which is B2. So this is the force on 1 due to the wire 2. So in magnitude, it's going to be then F12 is equal to the value of B2. So it's I1 L1 L times the distance between them times the magnetic field, which is mu naught I2 divided by 2 pi d. Obviously, these two forces have to be equal in magnitude, and there is a fundamental reason why that should be, and you guys probably would have guessed it by now. I'll give you a moment now to guess it. Times L. So notice, F1, 2, namely the force on the first wire due to the second wire, is equal to mu naught I1, I2 divided by 2 pi d times L. And F2 on 1 is equal to mu naught I1, I2 divided by 2 pi d times L. Again, it's an identical force. Again, we're going to define the force per unit length, which is in Newton per meter. F12 just divide by L, which is F12 divided by L. So the unit for this guy is still Newton per meter. Then it's going to be just the same identical expression, the product of the two charges divided by 2 pi d. I'm going to pause right now, give you about a minute or two to think about why these two forces, they must be the same. Are you still watching? You really should go and think about it. Okay. I'm going to tell you why that is, and that has to do with physics 1, namely the third law of Newton, action and reaction. Okay, so this basically the third law of Newton, and namely that these two objects are interacting, and if they do interact, if one of them exerts a force on the other one exerts a force that is equal in magnitude and opposite in direction, then the two forces are pointing away from the two wires. This is the repulsive force. In the case when the two wires are actually have currents running in the same direction, the same direction, we will see that the force is going to be an attractive force, and let's see why that is. Okay, I mean, magnitude wise there is nothing that's going to change. It's the only thing that changes is direction. So I have wire 1 has a current running through it, I1 in here, this one I2, both of them are in the same direction. They don't have to be, by the way, the same value. The two currents could be different values in the two wires, and the distance between them is d. So I'm going to make the case for the magnetic field due to wire 1. Again, it's going to be into the screen. So in this point, this is B1, just like before, B1, and we have its magnitude. It's 2 pi mu naught I divided by 2 pi times the distance between the two wires, and this distance is d. And the force then, which is going to be the resultant of the current going this way, and the surface is, I mean, the magnetic field is going into the surface of the screen, so this force is going to be this way. So the force on due to wire 1 is going to be pulling toward wire 1. The third law of Newton would make the case that the second force actually will be pushing it downward. Let's see why that is. The current is going this way in wire 2. So that means the magnetic field that produces is curling in this direction in such a way that at this point it's coming actually out of the screen. So in which case now wire 2, so this is B2, which is the same magnitude as the first one, except the current needs to be replaced. So it's mu naught times I2 divided by 2 pi times the distance. And now I have a current running this way, and the magnetic field is coming into the out of the screen. So the force is going to be pointing down, as we would have argued basically with the third law of Newton. Magnitude-wise, both forces will be identical, and the two forces will be equal in magnitude, as the third law would have predicted. Okay, this is a point I need to stop in here, and I'm going to make a few more points about this one. And this is an important result that we will need later on for our homework. Thank you.